Yes, I'm Ekta Patel. I'm a Hubble Fellow at University of Utah, and I have been tasked with the job of keeping you awake after lunch. No, I am going to be talking about the first half of some of what we know about the interactions between the clouds and the Milky Way. And you'll notice some of the plots that we've already seen today. So I might go quick on a couple of the slides. So as we started to hear today and a little bit yesterday, we're learning, especially in the last decade or two, that the LMC is quite massive. So for a long time, we were thinking the LMC was sort of in the 10 to the 10 solar masses range in terms of its entire halo mass. But more recently, with many different lines of evidence, only some of which I've put up here, we've started to learn that the mass of the Milky Way at infall into the halo of the Milky Way, I said the mass of the Milky Way, the mass of the LMC at infall into the halo of the Milky Way is about 10 to the 11 solar masses, which puts it at about 10% the mass of the Milky Way, in which case my whole talk will focus on how we have started to learn about the implications of the fact that the LMC is a massive satellite interacting with our own galaxy. So some of these lines of evidence we've already heard about, including mass modeling and about the internal kinematics of the clouds, about the binarity of the clouds, which I'll touch on some more. Some things I'll also talk about a little bit later are using the census of satellite galaxies to understand the mass of the LMC. And then, of course, we've seen this image on the right and many other beautiful images showing all of the faint structure that we've learned about more recently. That's really pointing to the fact that the LMC is definitely a few times 10 to the 11 solar masses. We've seen a version of this plot today. This is one from Eugene's paper from last year, which is showing several different studies that have, again, tried to constrain the mass of the LMC. And you see there's sort of a nice clustering between about 1 to 3 times 10 to the 11 solar masses. So keep that in mind as we continue to talk about how the LMC is influencing the Milky Way, and of course, also subsequently, all of the other substructure in the Milky Way's halo. So traditionally, the picture was that because of the existence of the Magellanic Stream through observations, that the clouds have been orbiting around the Milky Way many, many times, that they've completed multiple passages around the Milky Way. And these were some of the parameters that were adopted in at least one of the many studies that have studied the interaction of the clouds with the Milky Way. So in this particular example, a Milky Way potential of just under 10 to the 12 solar masses was assumed, as well as an isothermal sphere. So there's a flat rotation curve at 250 kilometers a second. And the LMC's 3D velocity that was adopted was around 300 kilometers a second. You'll also notice, speaking of the mass of the LMC and also the SMC, that these masses are about an order of magnitude smaller than what we are now starting to adopt in our models. So this is a sort of the traditional picture. The Magellanic Clouds are moving around the Milky Way, making multiple passages around the Milky Way, and that was thought to help to form the stream through tidal interactions with the Milky Way and the ram pressure of the Milky Way stripping gas away from these galaxies. But of course, as we fast forward to the more recent history, we have a lot more information about these two galaxies that allow us to provide a much more rigorous orbital understanding of these galaxies. And so I like this little schematic because I think it kind of puts in a visual sense the sort of basic way that myself and many others before me have thought about integrating the orbits of the clouds, where we model the Milky Way as a 3-component potential, so a bulge, a disk, and a halo. And I will say that we all kind of have our different favorite model for the halo. In my models that I'll talk about, I adopt an NFW halo, so it's a sphere. There's usually an LMC of some form. In some cases, it's a point mass. In some cases, it's an extended mass distribution. In my models, it's an extended halo, including a disk. And then there's also an SMC, which again is also an extended mass distribution. So if you build an orbital setup where you model the gravitational potentials of all these galaxies, and we use this very precise 6D phase space information that Nitya and others have gathered, mostly using HST, we can integrate equations of motion and figure out what is the most likely orbital history for the clouds within the uncertainty of this measured 6D phase space. So of course, this requires assumptions. So the assumptions we're making are what is the mass of the clouds, what's the mass of the Milky Way, importantly, and then looking at what's the sort of distribution of orbital histories that comes out. So if you adopt these parameters, and again, this will vary depending on what your your Milky Way mass and shape are, et cetera. But at least in most cases, you will get the LMC on first infall, as many of us have already mentioned throughout the last couple of days. So I just want to point out a couple of things about this orbit and also just explain this figure on the right because you'll see it a couple of times. So on the x-axis, you're looking at look back time. 0 would correspond to today. And on the y-axis, you're looking at relative distance. In this case, the LMC's orbit is, of course, plotted with respect to the Milky Way. And then as I go forward, if this goes forward, okay. Oh, right, so this is, of course, on first infall, and the LMC has just passed through the pericentric passage about 50 million years ago, arriving at its current position at 50 kiloparsecs today. Of course, we also know that the SMC is adding complexity to the situation. So we think the SMC's orbit is in a binary situation with the Large Magellanic Cloud, and perhaps in a situation where it's been a long-lived binary with the LMC as well. Now, I said a little bit about the mass of the Milky Way, and I just want to point out and harp on this for a second, even though it's not really a Milky Way conference that we're at, but it is our biggest pesky neighbor, at least in terms of the XMCs. And so I want to harp on the fact that the mass of the Milky Way is actually one of the critical unknowns in what you get for the orbital history of the clouds. And so much so that a lot of reasons why some of our models come out to be different is just because of the Milky Way mass we assume. So this is the sort of picture that I've just presented. I'm just adding in a couple more lines for different LMC masses. Everything else is exactly the same. And so you see again that there's this long-lived, oops, that's not what I want to show you yet. Well, the pointer, which is there. Okay, so you have the long-lived LMC SMC binary, and then you have the LMC on first infall. There's one pericentric passage for the LMC. However, if you increase the mass of the Milky Way by 50%, you get a very different orbital history. You get this two-passage scenario where the LMC has made a passage about 4 billion years ago, and also, again, in the very recent past. And the other big thing that changes when you bump up the mass of the Milky Way is that the LMC and SMC are no longer a long-lived binary. So just based on changing one parameter here, but quite an important one, we do get these very different orbital histories. And I think that's one of the reasons why there's been some complications in the census that we can all come to as a community. So I will not say too much more about the mass of the Milky Way, but I'd say that we're starting to converge to a place where at least getting to about a 30% uncertainty, so maybe not quite as much as the factor of 2 that's shown here, but that's also certainly an area of work that's really important. Even if we're not talking directly about the Milky Way in this conference, it's intimately related to this issue. So as I said in summary, there's these two possible answers. Statistically, when you account for all of the uncertainties on the 6D phase space, you will get the first infall passage much more often. And then you will get this second long period multiple passage orbit at the sort of single-digit % level. So from a statistical point of view, the first infall is still favored just by the choice of proper motions. Okay. Another thing that we've learned in about the last 10 or so years is that because the LMC is as massive as 10% the mass of the Milky Way, it has a very large impact on what happens to the Milky Way as the LMC comes through the halo of the Milky Way. So in this nice little graphic here, what I'll show you is, of course, the LMC starts outside of the halo of the Milky Way. So it's essentially starting at the Vero radius about 2 billion years ago. And as it passes through the Milky Way's halo and arrives at its position today at 50 kiloparsecs, you'll notice that the two numbers I've written here are the masses enclosed within the Milky Way at 50 kiloparsecs and the mass of the LMC at 50 kiloparsecs. And those numbers are only different by a factor of a few. And so, of course, there's a really important two-body encounter happening here where the LMC is even in this rigid potential. So this is not a representation of individual particles representing the Milky Way, but quite literally a rigid potential where you're just allowing the center of mass of both the Milky Way and the LMC to move. You find that the LMC is actually moving the center of mass of the Milky Way by a few tens of kiloparsecs and also giving it a velocity shift that's quite high, in this case, 75 kilometers a second. These numbers are all from a paper by Facundo Gomez from 2015. Another thing that we notice here is that the barycenter of the Milky Way LMC system is also going to move. And so just the simple idea of the fact that the LMC is a 1 to 10 mass ratio interaction has a great impact on the Milky Way, and therefore our understanding of the dynamics of literally everything else that's also moving through the Milky Way's halo. And like I said, this is just in sort of the rigid potential assumption. So you can still just think of these two things as spheres that have moving centers of mass. So we're not yet in the more complicated picture. So one point that I just want to make is that as we make these kinds of dynamical models, we have to account for the fact that the Milky Way is responding to the passage of the LMC as it falls into the halo of the Milky Way. So I'm going to give a little example of how much that affects other substructures. And I know that's, again, not the main focus of this conference, but because it has such a large impact on everything else orbiting the Milky Way, I think it's important to point out. So here I'm showing another figure, just like the ones you saw before. So x-axis is still look back time, and the y-axis is distance from the Milky Way center. And here for my example, I'm using the Carina dwarf galaxy. So one of our favorite classical dwarf spheroidals orbiting around the Milky Way. And you could say for this purpose, it's about 10% the mass of the LMC, right? So we've got a Milky Way, the LMC is 10% the mass of that. Carina is 10% the mass of the LMC. So many 1 to 10 ratios here. So what I'm showing here is the orbit you get for Carina, and that same kind of orbital setup I was explaining. If you keep the center of mass of the Milky Way fixed, so in other words, it is not experiencing the gravitational influence of the LMC. And then when you simply allow for that center of mass to move around as it reacts to the LMC, you get a very different orbital history. Okay, so this is comparable to the kinds of uncertainties you get when you change the mass of the Milky Way. So it's comparable to the extremes of the proper motions of Carina and what that would give you for the spread of orbital histories you would get. So this is not a negligible encounter here. And of course, different satellites will react differently to the effect of the Milky Way moving around, especially as we move into sort of the live time evolving potentials, which I'll get to near the end of my talk. So again, the LMC's dynamical impact on the Milky Way center of mass is very important to consider as we try to understand not just the global accretion history of the Milky Way, including the clouds, but also all of these other substructures orbiting the Milky Way. Related to that, I just want to give some results on some of the smaller, peskier dwarf galaxies that have not quite been mentioned, but have sort of been alluded to in the last couple of days. And so I want to spend a little while talking about satellites of the clouds. So as many of us already know, there's been tens of new dwarf galaxies discovered in just the last decade around the vicinity of the LMC and SMC. And I like this picture because it kind of nicely shows where some of those are located. These are all in the ultra faint dwarf regime. So we're talking about at their most massive end, these galaxies have 100,000 solar masses worth of stars. Nevertheless, these galaxies are in this region, and naturally it sort of begs the question of, well, do they have any association to the clouds because they are in such close proximity to these galaxies? And thanks to many of these discoveries came out in around 2014, 2015, and then just a few years later, Gaia DR2 was released, and many different teams, including many folks who were in this room, went ahead and took proper motions for all of those galaxies that were bright enough to do so. And with that information in hand, so we have this wealth of 60 phase space information for satellites. We have these orbital models that we've been using to understand the orbits of different substructures around the Milky Way. We can then ask this sort of deeper question of which of these satellite galaxies are actually dynamical companions of the clouds. So we're now moving into this sort of satellites of a satellite regime. So just bringing back this graphic on the right side, the results I'll talk about, or at least one of the set of results I'll talk about are really based on this similar sort of methodology here, where again, we're using these rigid potentials, but we are including the fact that there's the gravitational influence of the Milky Way and the LMC and the SMC, and now the smaller ultra-faint dwarf that would be considered as a potential satellite of the clouds. So I'm not the only one who's done this. There are several other people who have looked at different ways to characterize if these ultra-faint dwarfs are satellites of the clouds. So in my models, we do the same sort of methodology where we're calculating orbits and thousands of them to span the entire uncertainty of the 60 phase space and looking at which ones are most statistically common, and applying a diagnostic where we see which of these orbits look like they have a shared orbital history with the LMC. And when I say shared orbital history, I don't mean just visually, but also ones that imply that these galaxies have made a pericenter within the tidal radius of the LMC, suggesting that they've been gravitationally dominated by the LMC, and also having a velocity that implies that these are galaxies that have been bound to the LMC. So to give you a little bit of a synopsis of several of the different studies that have looked at this, all of these studies are written out down here in case you're wondering what they correspond to. This is one by Nitya, where she compared the 3D kinematics of some of these ultra-faint dwarfs to simulations. This is one by Dennis Urkel, where they looked at the orbital energy of these dwarfs. This is mine, where we looked at the orbits and the dynamics of the spread in the orbits you get. And then you'll see as time goes on, there's also some studies with Gaia DR3 as that's become available as well. And so we've come to a bit of a consensus, I'd say, that we think that there's, of course, the SMC, that's a satellite of the LMC. And then there's these 6 other dwarfs that seem to be, at least in a variety of different ways, dynamically associated to the LMC as well. There are a couple of others that have been debated more recently. So there's GRU2 and Tucana 4 that I'd say are still kind of uncertain as to whether they're satellites. But I'd say in general, we're reaching a point where our confirmations here are in line with what's been predicted from cosmological predictions. So by looking at different subhalo abundances in simulations and counting up how many satellites you would find around a 10 to the 11 solar mass halo, these are all very much in line with what those suggest. When I say these definitions of satellite vary, I think this is a very important but maybe overlooked point in the community. If you're interested in satellite galaxies of the LMCs or really any other galaxy, I encourage you to look in the literature about what different definitions people are using. Sometimes it's purely a cut at distance relative to whatever host galaxy you're interested in. Sometimes it's more of a dynamical argument. Sometimes it's not. But I would say this is one area why we might be getting some different answers. So I like to show this visual. It gives you a nice representation of these satellite galaxies. So here you're looking at orbits being integrated forward in time. We have our Milky Way sphere. The thick white lines on the right side are the LMC and SMC. And you see the 6 pink lines that are intertwined around those two. And those are those 6 satellites that we're suggesting are satellites of the clouds themselves. And the right side just shows another sort of graphic of the same set. Okay, so we're finding that there's these ultra-faint dwarfs. We can learn more about the clouds from them, just even like I was saying earlier, what is the LMC's mass? Of course, there's a lot more rich information we can learn from these galaxies, and even other ways that we can confirm that they actually might have an association to the clouds outside of just their dynamical histories. So one example that I want to show is this analysis by Elena Saki, where she looked at some deep HST data for many of the ultra-faint dwarfs around the Milky Way, but she was able to separate them into 2 different groups, one that seemed to be associated to the clouds and one that do not seem to be associated. So the left are the ones that are associated to the clouds and the right are the ones that are purely just Milky Way satellites. And what she found is that the satellites that seem to be associated to the clouds are quenching about 600 million years after the non-LMC counterparts. And so we're even starting to see signatures within the star formation histories, even for galaxies that have all quenched pretty much at reionization almost, that this host environment is still playing a role because these galaxies are interacting with the clouds before the clouds enter into the Milky Way's halo. And so there's some pre-processing happening there. Okay, moving on from there, I want to go to a little bit of a more of a realistic picture because I kept on talking about rigid potentials and we all know that's not the real truth. And so how can we make our models better to actually account for sort of global impact that we know that the clouds are having on the Milky Way? Eugene will talk a lot more about this in just a few minutes, but I just want to touch on a couple of things. So we know that the potentials of the Milky Way and the LMC are not rigid in time. This is a nice simulation from Nico where he's shown, you're seeing the LMC's orbit as the white line and the contours that are shifting as this movie plays are showing you the density contours of the Milky Way's dark matter density as the LMC is interacting with the Milky Way. And you see you start to get this oblong structure towards the right side of the movie. And that is all purely because the LMC is changing on large and small scales. When I say large, I mean, you see the 100 kiloparsec marker. So out to 200, 300 kiloparsecs is affecting the global density of the Milky Way's halo. And so moving ahead, what we really, I think, should strive for as a community is to really account for these interactions in a much better way. So Nico's got these great simulations. They represent a lot of what we already know in terms of matching the 2D kinematic or the 3D kinematics of the clouds, accounting for all of the shifting of the center of mass of the Milky Way. And this figure on the right is just another visual of how that density field is perturbed. So this is the Milky Way halo after it's been perturbed by the LMC. The dark blue contours are over densities and the lighter colors are under densities. And so the aim here is to account for all of this physical distortion as we integrate the orbits of substructures around the Milky Way. So I'm gonna actually skip this next slide, but you can ask me about it later. But I want to end with, I promised to talk about cosmological analogs and analogs in the field as well. So I just want to end with, we have our great examples very nearby, but how do we actually put those in context? Right? What do we have when we look out into other Milky Way-like systems or even into the field for other LMC or SMC-like galaxies? So several people have looked at this in simulations. So using your favorite suite of simulations, I'm sure somebody has done it, but this is just a selection of results. If you're looking for a mass analog of the LMC, so just looking for that 1:10 mass ratio, you're not restricting by position, velocity, et cetera. About a third of Milky Way-like galaxies have a massive satellite. If you then further restrict by your favorite criteria, let's say in this case, by looking at the massive satellites within 50 kiloparsecs and at very high speeds, of course, your statistics go very close down to zero. And so I put these numbers on the bottom where you really don't even have, even in these big box cosmological simulations, that many analogs of Milky Way LMC-like galaxies. Nevertheless, if you add an SMC on top of that. And I just want to make the point that Gertina said earlier today, which is that for the LMC and SMC to be a binary, the clouds must be on first infall, and that's in line with a lot of the work that's been done in these simulations. The last thing I will tell you is about observations, of course. And so, again, many folks have looked at what's the frequency of an LMC-like galaxy around a Milky Way. And again, these have different criteria for how they're characterizing their Milky Ways and characterizing their LMCs, but they're roughly all in line with each other. In SDSS studies from 2011, 2012, about 40% of the L-star galaxies had a bright satellite within 250 kiloparsecs. There's certainly a lot out there that we can compare our own system to. But of course, if you limit down to having the right position and velocity, you're going down to just a few percent. The right side is showing you some very new results just off the press that are not yet published. So this is from the SAGA survey, the satellites around galactic analogs. So they're looking at Milky Way-like hosts and the satellites around them. And this is from their upcoming third data release. And they're finding that about, again, a third of their hosts have a satellite that's above 10 to the 9 solar masses. And they're generally a little bit further than the LMC is, which is being shown in that first image on the right side. However, there was a recent study that shows, based on simulations, that often LMC analogs get bluer as they enter the halo of their galaxy and then rapidly redden just a couple billion years after that. So this picture might still be consistent between the observations and simulations. So I am very much out of time. So I'm going to leave you with my conclusions, which are that with the 60 phase space information and orbital models, we can statistically show that the Magellanic Clouds are on their first infall into the Milky Way. The LMC certainly has a non-negligible impact on the entire dynamics of the Milky Way halo from large to small scales, including all the substructures that are related to the Milky Way. The clouds we know have a handful of satellites that enter with them into the Milky Way's halo. So this is the sort of first evidence of a group infall in a cosmological sense. And very, very importantly, I think in the last point is that for accurate comparisons to our own Milky Way and clouds system, we have to choose appropriate analogs in both observations and simulations. Because depending on how you slice the pie, you'll get very limited statistics, or you may not be able to answer your original scientific question. And so I'd encourage those who are interested in making comparisons to theory to be very careful on how you make your selection criteria if you want to understand the dynamics of these systems. So thanks for your attention.
Thank you very much, Ekta. Questions already here, Alex?
I don't know if we're still into this. Alex Riley, Durham University. You talked about, so going back to selecting your LMC analogs from the cosmological sims, based on dynamics.
Yes.
Does the scenario get a little better if instead of doing it on I guess you did like redshift 0 velocity and distance.
Yeah, I'm myself and others have done it both just at redshift 0, but also just to get more statistics going back at least up to low redshift, like 0.2. So that helps a little bit, but what's the rest of your question?
I was just gonna ask like if could you pull a percentage off of doing it if you did it on like Perry's, like just matching pericenter and apocenter reasonably well?
Like what do you get if you? So those were some of the statistics I was showing when you go down to like the 2, 3, 4% level, just based on Apo and Perry. I mean, you get very few that match the actual clouds. Is that what you're asking?
Yes.
Okay, yeah. But I do think there's something to be said about using mass analogs, but again, depending on what your science question is, right? So it's still useful to know what how those 1 to 10 mass ratios are evolving.
Andy Fox, Space Telescope. Thanks for the great review. I was really interested in what you were saying about the satellites of the LMC, and you had the 6 galaxies, you can plot their orbits. Do any of those satellites have enough mass that it actually changes the dynamics of the LMC or SMC, or can you ignore that effect because they're so small? Yeah,
you can pretty much ignore their effect. They're in these models, we still model them as like 10 to the 9 in halo mass. But yeah, it's not, it's not enough really to cause any major changes. Even the SMC. So when I was adding in, when I showed earlier how like if you just fix the mass fix the center of mass of the Milky Way versus moving it, and there's a big difference in the orbit of Carina. If you you could also similarly integrate just in a Milky Way potential and then add in the LMC and then add in the SMC. Even the SMC has a very small dynamical impact, and this is just then a order of magnitude lower. So it's minimal.
Thanks. And all this is based on proper motions. All these orbits are actual data.
These are all based, the initial input is all of the 60 phase space that comes from proper motions, line of sight velocities, distances.
Great, thank you.
Thank you. Cecilia Mateo from Modeler Montevideo. Thanks for the great talk, Ekta. You mentioned that LMC satellites quench 600 million years after non-LMC counterparts.
Yeah.
Is that a statement that comes from simulations, or is there an observational?
Oh yeah, no, these are observations. These are HST observations of these ultra-faint dwarfs.
Oh, that's very impressive, because measuring that difference in age at those very old ages, that is super impressive.
Yeah.
Thanks.
Yeah, I encourage you to look at that paper.
So questions from junior people are more than welcome.
Kat Barger, Texas Christian University. As many of us in this room probably know, that there's a lot of confusion on the formation of the leading arm, the leading possibly tidal arm of the Magellanic Stream. Could you say anything about any possibilities with respect to consistency with maybe like material got removed from leading satellite galaxies in the Magellanic system? Is that a possible scenario?
I mean, most of these ultra-faint dwarfs have no gas today, right? And they all quenched really long ago. So I think
quenched a long time ago.
Yeah. So you can see most of them reach like their 80% quenched or even 90% quenched like 11 billion years ago. So it's much earlier than the formation of the stream. And so I don't think there's any association there.
I see. Thank you so much.
Yeah.
Manuel Caderes, Book Chile. You mentioned how there's an effect on the dark matter halo of the Milky Way by the inflow of the LMC. How much would this change if you take into account the satellites or changes in the mass of the LMC, or possibly?
Yeah, you're saying so in the So I think this is a slide I skipped. First of all, I didn't mention that all of these models are run by Nico. So all of the simulation-based work is coming from his really great models. So I think this is what you're asking. How does a deformation of the Milky Way halo affect the orbits of satellites? Is that right?
How much? My question was the other way around, but yeah.
Do the satellites affect the deformation of the halo? Okay. So I think based on what I was saying earlier in terms of how the SMC has a minimal impact dynamically on the satellites, that if the SMC is not having that much impact, we don't think that even less massive satellites are going to have that much impact. So probably no on the deformation parts. Whether some of those satellites could be interacting with different parts of the density perturbations that we can't directly measure. I mean, there's a lot of complications there that could be interesting to look at.
Thank you.
Maybe time for one last question. What Eugene set up his laptop.
a really quick question for you, Nico, actually, from your the simulation, like if there was like some pulsing from the halo, that I'm guessing that's like not real. That's like maybe a computational
I mean, with the contours, you're looking at the contours.
Yeah,
This
yeah.
is me not fixing properly.
Okay, thank you.
specific
I just wanted to check. I was like, what am I not understanding?
Yeah, I fix that for us. No,
No worries. What's the question? Oh.
All right. So next we have Eugene Vasiliev talking about the dynamics of the LMC Milky Way system.
Okay, yeah, I will continue along the same lines, discussing the dynamical interaction between the Magellan system and the Milky Way. And as an illustration of the two systems, I plot here, show a plot from one of the Native Australian artists, a contemporary Native Australian artist, which I think shows something resembling LMC and SMC system. We can even see the stream between them, perhaps. And as another example of a culture that has not been mentioned yet so far is the names of the Magellanic clouds in the Maori language, which I find quite exciting. My favorite one is actually Tika Takata and Ti Ore Ore. And there is a whole paper about the discussion of the names of the system. And so Ekta already introduced the fact that the LMC is quite a considerable neighbor of the Milky Way, and all the numbers that we have here illustrate that it might be quite dynamically important. It's only between 5 and 10 times smaller than the Milky Way itself. And nevertheless, even though the ratio is quite high, but as we can see, the effects that we can measure at the current level of precision are significant and should be taken into account. The first thing that I want to discuss is the effect of the LMC on the stellar streams. By now, we have 25 years after the discovery of the first stellar stream in the Milky Way's halo, that is the Sagittarius stream. Now we have almost 100 of them, thanks to compilation done by Cecilia. We have a lot of information about these streams. And basically, the streams are produced by tidal disruption of star clusters or dwarf galaxies. And they are very sensitive probes of the gravitational potential of the Milky Way, among other things. And one of the things that came out recently, like a few years ago, was the impact of the LMC on the streams, which I could illustrate with this movie by Dennis Erkel, which has simulated the formation of the Orphan Chenab stream. As you can see, the stream just happily unfolds along its orbit until the LMC comes into play. And LMC passes relatively close to the trailing arm of the Orphan Chenab stream. And what happens is that it deflects the stars from their original orbit. And that deflection is actually measured. And the way it is measured is by looking at the deviations between the direction of the proper motion vectors and the direction of the stream track. Because normally, if stars are lost from a stellar system, they would travel along more or less the same orbit. But if there is any dynamical perturbation that comes into play, then the motions of the stars will be misaligned with this stream. And that's what we see here. We also the models predict that there should be a huge kink in the stream track, which I think now they have a hint of being observed, but I think it's not official yet. And another stream which displays very similar, well, not very similar, but comparable amount of perturbation is the Sagittarius stream, which is the largest stream that we have in the Milky Way's halo. And to illustrate it, we have a lot of data on it, but to illustrate the differences between the stream models, including the LMC and not including the LMC, I highlighted here two areas where the differences are most important. So this is the side-on view of the galaxy when the Sagittarius remnant is sitting just slightly below the galactic plane and behind the galactic bulge. And the leading arm of the stream if you include the LMC in the model of the stream, you can fit it much better than when you don't include it. So when you don't include it, the orbit doesn't match the observations. And even more conspicuously, there is also a similar kind of misalignment between the stream track and the direction of the proper motion vectors. And again, you need to include the LMC in order to match this. But the interesting thing is that unlike the orphan synopsis case, the effect of the LMC on the Sagittarius system appears to be most important in the leading arm, whereas, as we all know, LMC is in the southern hemisphere, but the most of the effect comes in the northern hemisphere. So why is that? And here we come to the second question, and the question is, what impact does the LMC has on the Milky Way's halo in the global sense, not just the local deflection of things, but in the global perturbation things. And I'm going to play a movie that is kind of similar to what Ekta had already shown, where we have an interaction of the Milky Way and the LMC. So you could guess that LMC is the smaller of the two guys, the one coming from the left. And I'm plotting here this interaction with the velocity vectors of particles in the simulation. And both galaxies orbit each other. So it's not that LMC is orbiting the Milky Way. Both galaxies orbit the common center of mass. And what is more important, though, is that they're not orbiting as rigid entities. And as the LMC approaches the Milky Way, you see that the Milky Way's halo, shown here in the red contours, starts to be distorted. So this is like this overdensity behind the LMC, which is essentially the trail of the dynamical friction. And the velocities of stars in the Milky Way halo also start to point towards the orbit of the LMC. And as we arrive to the present day position, which is here, you could see that the Milky Way halo actually has been distorted quite considerably with respect to what it had been originally. And now, remember that we are observing this whole thing from the vantage point of the Milky Way disk. And on this scale, the Milky Way disk is just here. It's like a very small speck in the center. So if you transform into the reference frame centered on the Milky Way, we have to subtract the velocity of the Milky Way's center, which is directed more or less downwards. And when we do that, what happens is that now everything else is pointing upward. So the inner part of the Milky Way move with the same velocity as the Milky Way center. When we subtract this velocity, the inner part does not get distorted, but the outer parts move with a different velocity. And what happens is that with respect to the Milky Way center, the outer part of the galaxy kind of moves up towards the northern hemisphere. And this motion is could be seen in the kinematics and also in the density, because here I'm again plotting the comparison of the equidensity contours. The dotted lines are the original undistorted halo, and then the red lines are the lines for the Milky Way halo as has been distorted by the LMC. And well, they don't match each other. And this same picture, like the brain tomography that Ekta was showing from Nico simulations, illustrate these two aspects of this distortion. So there is a local wake from dynamical friction, which trails the LMC on its orbit. And that's a kind of classical effect. But a much less obvious effect is the global distortion, which has this dipole type of perturbation. The northern part of the galaxy has overdensity because the inner part of the galaxy has shifted downwards with respect to the outer part. And the outer part has much longer dynamical time, so it did not have time to react. It kind of stays put, whereas we are shifting down. So what happens is that now the stars or particles that had been at a distance of 100 kiloparsec, now they find themselves at the distance 120. And of course, their density that was originally at 120 is lower. So now there is an overdensity just because we are shifting the vantage point, the center of the Milky Way. And in terms of observable predictions, what we would see in the sky when you look at these distortions, you could split them into density distortions and kinematics. And again, in the density, here is like the sky plot, what we could have seen if we had access to non-distorted structure of the Milky Way halo. We would have seen overdensity of stars along the past orbit of the LMC. So on this part, so this would be galactic plane sitting here, LMC is here, and along the past orbit of the LMC, depending on which slice in this distance you get, you would have seen overdensities. And these global distortions would mean that in the upper part, in the northern hemisphere, we'll have overdensity of stars. In the south, we'll have underdensity. And because the whole thing is moving upward, we would also see this in the line of sight velocities, which is the second panel. Stars in the southern hemisphere are predominantly moving towards us, whereas in the north they're moving away, and in the proper motions. And in the proper motions, again, the B component of proper motion, which is the component along the galactic latitude, you would see that everything is moving up. So these are theoretical predictions that have been put forward by several groups already. And they have been confirmed by some observational evidence in the last few years. First to come the evidence from the kinematics of stars in the outer part of the galactic halo, kinematics of galactic satellites and global clusters. And everything here points towards the velocity offset in the vertical direction of a few tens kilometers per second, consistent more or less with the predictions of the models. And also there is an evidence of overdensities in star counts, although it's not as straightforward because there are also contaminating factors like the presence of Sagittarius stream or the overdensities coming from the earlier accretion events in the Milky Way history. But there is some evidence in forward of this. Unfortunately, there is so far no evidence in the proper motion. So that's something that has to be confirmed in the observations yet. An interesting thing is that these perturbations are actually quite sensitive to the anisotropy, velocity anisotropy of the Milky Way halo. So that could be used as a very interesting probe of the velocity structure of the Milky Way halo. Notably, if the halo is radially anisotropic, the perturbations would be much stronger, both in density and also in kinematics a little bit more. So in density, will have much more significant dynamical friction-induced trail. And these all perturbations are, I was talking about them as if they were perturbations in the tracers, in stars that, or global clusters or anything else we could observe. But in principle, these perturbations also should come into play in terms of the gravitational potential. So Ekta was talking about moving the two galaxies around each other, but moving them as rigid potentials. But of course, since the galaxies are distorted, we have to think about what happens when we look at the forces that are induced by these perturbations themselves. So the non-perturbed galaxies, of course, they would have force fields that are directed more or less towards the center of each galaxy. And these perturbations that we have seen before would correspond to some sort of dipole-like perturbations for the Milky Way halo. So there is, again, there will be overdensity of stars in the south and general dipole perturbations in the north-south direction. But that would correspond to sizable additional accelerations. And same for the LMC, because LMC doesn't stay as a spherical system if it ever goes. It gets also just stretched, much like any other tidally perturbed system. So the LMC would also have some perturbations. And on top of that, we also have perturbations coming from the fact that the Milky Way is not an inertial system, because it's accelerated by the LMC. So when we are sitting in this reference frame, we have to account for the non-inertial forces. So in total, the velocity field, the force field of the galaxy would look considerably more complicated. And that is important when we want to study the orbits of any tracers, like, for example, looking at the orbits of stars in stellar streams. Here is a comparison. What would happen if you start integrating the orbit of a test particle backward in time in several approximations. First is the completely rigid potential. So there is no LMC, just the Milky Way. Second is the frozen potential, so rigid potentials in Ekta's terms, when these galaxies are moving around each other but not distorted. And then a full and evolving simulation where both galaxies actually start to be deformed. And then there is the true orbit, which in this case comes from the N-body simulation. And as we do it for several gig years into the past, you could see that the rigid Milky Way actually doesn't do a good job at all. Sorry, the no LMC case makes a very different orbit. But even the difference between rigid and deforming potentials starts to be quite important at the level of precision that we want to care about. Interestingly enough, you would need to take that into account when looking at perturbations of the LMC on the streams. And that's the work that has been some steps into, first steps into that have been done by Sophie Lengen a couple of years ago when she looked at the kinematics, predicted signatures of the perturbations of the distorting Milky Way and LMC on the kinematics of the orphan chin upstream. So in current studies, they are using bits which are performed in the moving potentials, but not distorting. But in principle, the sensitivity to perturbations in the distorted potentials is above the level of precision, so we should be able to measure it. But it becomes quite complicated. And as Ekta already has illustrated, that the masses of the mass of the LMC currently we converge to the values somewhere between 1 and 2 times 10 to 11 solar masses from different studies. The interesting thing is that streams could be used to probe the radial dependence of the mass, because each stream comes at a different pericenter distance to the LMC. So it gets distorted in different ways. It depends on both the pericenter distance and the relative velocity, which is shown here on this plot. So several streams from, I think from Nora's compilation, and she followed it up, the streams that she discovered in DS data, and then looking at how different streams would react. It seems that several of them actually are quite sensitive to the LMC mass, and they converge to more or less the same mass as measured from other probes. As a digression, I could also mention that the LMC has an impact on the mass measurements of the Milky Way. I think so far we probably are entering the era of more precision galactic dynamics. Maybe we are not longer at the level of factor of 2 difference, but at the level of maybe 20–30% uncertainty on the mass of the Milky Way and the mass profile of the Milky Way. So here is a compilation of studies using very different dynamical methods and probes. And among them, there are several studies that were based on streams and were taking into account the effect of the LMC, which is important because that biases if you don't take that into account, that biases the determination of the Milky Way mass by a couple of %. And the interesting thing is that there are a few studies recently that came up with these measurements of the velocity, circular velocity profile in the Milky Way disk, based on the GEANS analysis of the kinematics of disk stars. And they indicate that the velocity declines quite rapidly beyond, let's say, 20 kiloparsec. And that seems to be inconsistent with the measurements of the enclosed mass at larger distances. So if I plot a same potential model that matches the measurements in the outer part of the galaxy, that would not match the inner part. The question is why, and it's quite possibly the LMC is also a culprit here, because these outer parts of the Milky Way have well-known perturbations in terms of there is the warp and the warp that might be precessing, and the LMC might actually be the main factor that induces this warp. And in the future, the warp actually will become much stronger, but even now the LMC might induce some of these perturbations. I think I might skip on this part, which is the perturbations of the satellite orbits that Ekta already has shown. Basically, when you integrate back the orbits of satellites, including the LMC effect and not including, some of them don't change much, some of them change a lot. So for example, here, the Leo 1 is the galaxy that is one of the least bound to the Milky Way. And if you include the perturbation from the LMC, it turns out that the Leo 1 is actually on more bound orbit. So it helps to keep it bound, decreasing therefore the estimated mass of the Milky Way. But for some other galaxies, it's the other way around. Like Sculptor, for example, ends up much less bound. And there are even effects that go beyond the immediate neighborhood of the Milky Way, again, coming from the fact that the Milky Way center is shifted by the LMC with respect to any external system, including, for example, the Andromeda galaxy. So the Andromeda's center of mass, the Andromeda's relative motion to the Milky Way is actually the relative motion with respect to the center of mass of Milky Way and LMC. But we measure it with respect to the Milky Way. So we have to account for this extra perturbation by the LMC. And it turns out that these revises the estimate of the Andromeda orbit by a little bit, but that actually is significant for the purpose of so-called the timing argument estimate of the masses of both galaxies. So a couple of years ago, there were 2 studies that looked into this effect, and they converged to the idea that actually by including the LMC in the analysis, you revise down the estimated mass of the local group by quite considerable. It's not coming so much from the perturbation itself, but it comes from the fact that including the perturbation places the Andromeda on a less eccentric orbit, and that in turn affects some other calibration factors in the estimates. And one thing that I wanted to mention in the last few minutes is that the trajectory of the LMC is actually much less well known than we would like it to be. And the reason is because it's very, very marginally bound to the Milky Way. So any small changes in the adopted propo-motions lead to very significant changes in the LMC's orbit, as could be seen on this plot. So these are the selection of propo-motions from a few studies in the last few years. And the orbits might differ by more than a factor of 2 in orbital time. Inclusion or not inclusion of the SMC actually also changes the orbit considerably. And of course, the LMC mass also changes the orbit. And most importantly, the Milky Way mass, adopted Milky Way mass, if you change it only by 10%, that leads to the orbits that are very tightly bound or the orbits that are completely unbound. So last year I was writing the review about the Milky Way LMC interaction, and I was repeating this common statement in the literature that yes, the LMC is most likely on its first approach to the Milky Way. But then looking at these plots, I realized that that might not always be the case. So there might be scenarios where LMC actually comes on the second passage, where the first passage was many gigayears ago, between 5 and 10 gigayears ago, and at a pericenter distance that was considerably larger. So instead of 50 kiloparsec, you would have something like beyond 100 kiloparsec. And in principle, the plots that Ekta was showing are not inconsistent because she was only looking back in time for 5-6 years. But if you try to do this exercise for a longer time, you would find that there are orbits that come back to the Milky Way. And interestingly enough, these scenarios, that of course, it depends strongly on the Milky Way mass, but the present day properties of the distortions of the halo are very similar between the scenarios of the first passage and the second passage. So is there any effect that could be distinguishing these scenarios? And it turns out that, yes, there is a factor that might actually be explained by the second passage scenario, and that is the presence of the so-called kinematically coherent satellite plane in the Milky Way. Now we are talking about the fact that many of the satellites of the Milky Way have very similar directions of angular momentum. If you plot them on the sky, like directions of angular momentum, there is a concentration of galaxies along a preferred direction, which happens to be the direction of the LMC's orbital angular momentum. And even after you eliminate the galaxies that are currently satellites of the LMC, there is still an overdensity of things there. So what could have happened is that in this second passage scenario, if I plot the possible past trajectories of various galaxies and compare them to the trajectory of the LMC, which is shown here by this dashed purple line, some of these galaxies might be coming with the LMC, and then on the first passage, they would have been lost and then keep orbiting the Milky Way. And now they're in a completely different part of the parameter space, but they retain the same direction of angular momentum. And that would be true for galaxies that look nowhere like LMC these days, like LEOs, for example. And of course, that would be true for galaxies like SMC, which keeps being the satellite of the LMC. But I'm just going to play the movie that illustrates this possible scenario for some of the galaxies, where the LMC system is coming here, and then there are galaxies that have been coming with it, and then are lost. So now the LMC comes out, and then the only guy that still remains there is the SMC. But other galaxies keep orbiting the Milky Way happily. And now that scenario is kind of consistent with all the observational evidence that we have. So I think I'll finish on that. And here is the illustration of this kind of satellite plane and the possible past associations of the classical dorsoidals in the second passage scenario. So, but the jury is still out whether it's possible or not in the more cosmologically motivated context. Thank you.
Thank you very much, Eugene, for a wonderful talk. Question. Next.
Alex Riley, Durham University. So we've seen a lot of presentations about these very aspherical distortions that happen to the Milky Way's potential field. How, if you're in, let's say, a large spectroscopic survey that's trying to measure the mass of the Milky Way, how should the survey be quantifying this? Is it good enough to give it just a cumulative mass profile with an NFW underlying that modeling?
Well, the survey gives you the velocities. Quantifying the mass profile is the job of modelers, right? And the question is, what kind of models do you want to apply which account for these perturbations? I think it's entirely possible. That was one of these studies mentioned here, is Correa Magnus and myself, the study that looked at one of the classical dynamical modeling methods, but including this extra step of compensating the LMC perturbation by integrating back the orbits of tracers. In this case, these are dwarf galaxies and global clusters, integrating back orbits in the time-dependent potential of the Milky Way LMC system. back in time until the LMC was far enough, at which time you could assume that the Milky Way was kind of closer to equilibrium. But this is not the only possible method. I think it is the way forward is to analyze whatever data we have and then try to match it with live dynamical system, not necessarily a body simulation based, but some sort of method that takes that into account.
David Niederber, Montana State University. Thanks for the great talk, Eugene. I really found your second passage scenario and the impact on the plane of satellites very interesting. I was just wondering, you know, if we're looking back at the Milky Way 10 gigayears ago, like how has its total mass evolved since that time, and how important is that?
Must be important, yes. And I did some very quick estimates on how would these past orbits change if the mass of the Milky Way was growing in time in kind of cosmologically motivated fashion. And the difference is again of the same order as the inclusion or not inclusion of the SMC, or inclusion of not inclusion of the kind of LMC, massive LMC with respect to a point mass LMC. So it is of the same order as the scatter. That makes it more complicated in the sense that we have several factors to disentangle.
If I think we have a, oh wait, yeah, Nick.
Jake Neibauer, Princeton. Thanks for the talk. For the two passage scenario, I was curious, is there any evidence in your simulations that the LMC sheds more mass than you would expect with just one passage? And is that, could that be confused with GSC debris in the outer instance?
Well, sure, there is evidence. I'm not showing the plot here, but generally LMC has lost half of its mass on the first pericenter passage in these trajectories. And of course, to make it consistent with the present day estimates, I'll have to start with LMC that was already 2 or 3 times 10 to 11 solar masses. And the debris from the LMC now are, I would say, well, this is the distribution of orbital debris colored by, well, the contours show where the density is. And it is perhaps resembling what we have from the early merger in the GSC. I think the very thrilling scenario is that both the GSC merger and the LMC came from the same cosmic filament, in which case it would be even more difficult to disentangle, but that also is quite possible.
I think we have a question online from Yumi. Yumi, I think if you unmute yourself and ask the question, we should hear you. If you want to try.
Okay, can you hear me okay?
Yes.
Okay, yeah, thank you for this talk. So if you, in your over density prediction plots at different distances, can you comment on the predicted over density on the Magellan Extreme, orbit, or positions?
Over densities of the Milky Way scale or over densities from the LMC stars?
Yeah, Magellan Extreme, like gas and probably stars too. Yeah.
I'm not sure I'm qualified to comment on that because all the simulations that I was discussing here are essentially pure embodied. There is no gas in it. So I don't know how much gas changes the kinematics. I hope we can hear about it maybe in several talks later this meeting.
I have a question.
Yes.
So in the second passage scenario, what happened with the SMC? Because I think they have a lot of pericenters around the LMC. Is there any observational signature that we should see?
SMC, in this case, it happily orbits the LMC since back then in time. But of course, the big caveat here is that SMCs, as much as all other galaxies are, in this case, are just point mass. If the SMC is a more massive thing, then it will be originally on less bound orbit. In principle, it could have been somewhat disturbed by the first passage scenario. The thing is that because the first passage occurred at much larger pericenter distance, none of the currently bound satellites to the LMC suffer in any sense from it. It's only the satellite that I listed. There's some of the classical dwarfs that could have been stripped, but none of the present day satellites are in any way affected, including the SMC, except that the case that the SMC orbit was kind of less bound in the past, which is not accounted for here. I think it is still safely inside the kind of region of gravitational influence of the LMC to be still bound and not affected by the first passage, but yeah, it remains to be shown.
The structure of the SMC should be different in the second And first,
I'm not sure. I think the business between two Magellanic clouds is their own thing. It's that they're not much affected by whatever happened to the Milky Way.
Danny Orta, CCA. Thanks, Eugene, for a great talk. So in this welcome back scenario, could you constrain it based on the star formation peaks that people are finding and look at it from that side of things?
Mm-hmm.
Would you expect the same kind of peaks in star formation history that you see in the Magellanic clouds from the two?
Well, I think as we have discussed this meeting, most of these peaks are concentrated in the last couple of billion years, and most likely are related to the interaction between the two Magellanic clouds, given their synchronicity. I was quite happy to see in David's plot in the first day that there was a hint of a peak at 6-8 gigayears back in time, which might well correspond to the first passage of the LMC, but I think it's very tentative.
Just to follow up on David's question, if you also have to have a massive LMC in the second pulp scenario, then aren't you looking more at a sort of one-to-one merger between the proto?
Well, it's still not to one-to-one, but it's more like 1-4, maybe 1-5. Yes. But again, the caveat here, I'm not starting from a cosmologically motivated Milky Way that grows with time due to the accretion of things, but it's like very isolated, well-prepared Milky Way, well-prepared LMC, and then just meeting in a nice formal setting.
So I have a follow-up question on the SMC interaction thing. So when I'm thinking of the SMC interaction, so like it's a lot less massive, but at the same time, it's like 1/10 the mass of the LMC, and then the LMC is 1/10 the mass of the Milky Way. And so then there's like looking at how the Milky Way and LMC are affecting each other, but you have it's like a 1-to-110 ratio for those two galaxies as well. So then I'm just thinking like, wouldn't their distortions be on par when they get close to interaction with each other? When they're far away, maybe not, but when they get close.
I see, the distortion of the LMC caused by the SMC?
Yeah, exactly. So is it a good idea to estimate the SMC as a point source when it gets close to the LMC? Do you see what I'm getting at?
Yeah. Well, as you could reckon on some of these plots now, or these plots perhaps. Well, yeah, it's kind of faint, but you see that the distortion of the LMC is massive. It's like not 10%, it's maybe 50% factor, right? Unless you're looking at the very inner part. So I would think that SMC is probably minor effect on it, but I skipped over it, but I think the effect of the SMC, if you include it in the model, is significant. It might be significant even if it is included at 10% level. And the reason is because now what we want to match is the present day position velocity of the LMC with respect to the Milky Way. But if the two galaxies were orbiting each other, then we should be matching the center of mass of both galaxies. And that affects the inference of the past orbit of the LMC at the same level as changing the LMC mass from 0 to 2 times 10 to 11 solar masses. Yeah. And that's again because the LMC is so weakly bound that even 10% changes lead to like 100% changes in the inferred past orbit.
Yeah, because one of the issues I'm thinking of too is that even if the SMC does impact it, it only impacts it when they're close, and they're only close when they're close to the Milky Way at the same time. So,
yeah.
Can you show your movie again?
Yeah.
Okay, this one or?
Yeah, that one.
Yeah. Yeah, share, yes. If it's clear.
It's on your webpage, no? So people can download.
Yeah, it's some. I think it's actually published along with the paper. I hope it should be at least, but it's also on the webpage.
Thank you. I just wanted to see it again.
Okay, so let's thank Eugene once again.